The object of this experiment is to find the focal length of spherical mirrors, both concave or converging and convex or diverging. Let's start with the concave mirror first because that's by far the simplest. You should know that when the object of a spherical mirror is located at the center of curvature, the image also forms at the center of curvature. That makes this concave mirror, which provides a real projectable image, particularly easy to find the center of curvature of. We have the object, which is our ray box, on a tilt table, posted post holder, and our concave spherical mirror is on a base posted post holder and mounted in a bar type lens holder. This is so that we can slide it easily back and forth. All we need to do is to find the location of this mirror that will project a clear image at the same location as the object. And we just do that by sliding back and forth. The distance now between the object and the mirror is the radius of curvature of the spherical mirror, and the focal length is half that distance. Of course, you can do another quick check on the focal length of a converging mirror by imaging something that is at a large distance, like the world outside, and that image will form at the focal point. So I've cracked the shades a little bit in that direction, and I'm taking the mirror and focusing it onto a card, and you can see that there is an inverted real image of the outside world, and the distance between the card and the mirror is approximately the focal length of the mirror. The focal length of a convex mirror is a little bit trickier to find, and in fact I encourage you to look at the web applet referred to in the lab write-up so that you can see by ray tracing exactly where the light is going. What we're going to do, as with the focal length of a negative lens lab, is to use a positive converging lens to create an image that will then become the object for the mirror. I have here the ray box, which will serve as our object. Ray box is on a tilt table on post and post holder. And here I have a converging 10 centimeter focal length lens. That lens is creating an image at this location. And I'm going to mark the location of that image because this image will become the object for my convex spherical mirror. As with the concave spherical mirror, if I put an object at the center of curvature of this mirror, the image forms at the same point, at the center of curvature. The problem is the center of curvature is behind the mirror. So I'm going to place this mirror approximately one radius of curvature away from the object, and an image is now formed at this location. Well, what does that mean? That means that if I look into the mirror, I could see a virtual image right here. Well, that's kind of difficult to do, and it would be very difficult to measure. So how are we going to find out, how are we going to ultimately come up with a measurement of the radius of curvature? Well, the light that's forming this virtual image, the light that appears to be diverging from that point, is actually being reflected from the front surface of this mirror, collected by the lens, which then forms an image at the same location as the original object. So all I need to do is to move this mirror back and forth a bit until I see an image forming directly under the object. Then this distance here from the original lens image location, which is also the virtual object of this mirror, to the mirror itself is the radius of curvature of this mirror, and the focal length is half.